This is my second video that I'm doing in my module on inverse trig functions, specifically in right triangle application type situations. So I'm just going to run through three quick examples on this one and how to interpret the results and how to write the equations and solve them. So starting with this here, what we're trying to do is solve for the unknown angles in the following right triangles by using inverse trig functions. You'll notice that each of these triangles are triangles A, B, and C, and you'll also maybe notice that they're not very clear when you see them here. So I'm going to kind of trace over them here, but this side here, we'll refer to this as 9 units in length. We'll refer to this side here as 5 units in length. But our intention here is to find the unknown angles in this triangle. So we're just going to pick one of them. As a matter of fact, I'm just going to go ahead and go with the base angle down here. But recall that knowing that this side across from our angle theta is 5 and that this side adjacent to it is 9 kind of gives us an insight into how big this angle might be, or at least it would tell us that it's less than 45 degrees, but we intend to find the exact value of this angle. So the first thing we want to do is we want to relate this angle theta to these two sides of the triangle that we actually know, and we say, well, which trig function will allow us to relate this angle theta to this side here and this side here? Well, in this instance it would be opposite over adjacent. So for example, we could start with the equation tangent. Okay, so tangent of our angle theta, which we do not know, is equal to our opposite side, which is 5 over 9. And in order to solve this, we're going to have to undo this tangent here using an inverse tangent function. So we're going to take tangent inverse of everything on the left, which was our tangent theta here. We're just going to drop this in. And then we say that's equal to tangent inverse of everything on the right, which happens to be this 5/9. The nice thing about inverse trig functions is that they cancel each other out. And what we're left with is just this angle theta. So we say angle theta is equal to this tangent inverse of 5/9, which really, you can look at it this way. Tangent inverse is the angle, and it's saying I am the angle that when you take the tangent of me, you get 5 over 9. The nice thing now is we can actually just get our calculators rocking. And I'm going to flip this back over to degree mode because we tend to interpret right triangle application situations more often with degrees. But we say in order to evaluate this, we'll just say we'll take 5 divided by 9, that value, the tangent inverse of this. And so we get about 29.1-ish degrees. So we say theta is approximately 29.1-ish degrees. And we say, well, would this be reasonable? Well, I would always encourage us when we find an unknown value of a right triangle to go back and put it up in the picture. But I say, yeah, you know what, this would be entirely reasonable. It's just shy of 30 degrees. And this was opposite our shortest side of the triangle, so it should be the smallest angle. And then as far as finding this angle up here goes, we could just say, well, it is 90 degrees minus the 29.1 that we just found, because these two angles must be complementary. So what we just got on our calculator, to make it really, really easy for ourselves here, we could just say minus 90, even though we should have a positive value there. It's positive, but we say about 60.9 degrees. So this would be about 60.9 degrees. So, really good example to start with. We use the tangent function to relate theta to the two sides. In this next instance, just to be clear on this one here, we're saying that the hypotenuse has a length of 6.4 and that this side down here has a length of 4. We are unaware of what this side length is, but that's okay. We don't need to know what the side is to go ahead and find, say, this base angle A. So we could say, all right, or theta. Actually, let's go with A on this instance. We say this angle A. We could say, well, which trig function would relate this angle A to this side and this side in my triangle? Well, this would be my adjacent side and also my hypotenuse side. So adjacent over hypotenuse, this would be our cosine function. So we have the cosine of our angle A. We don't know what A is, but we know that we get this. We get 4 over 6.4. So again, we could take the cosine inverse of both sides. We say cosine inverse of everything on the left, so cosine A, and that's equal to cosine inverse of everything on the right, which is 4 over 6.4. And then we could just evaluate this on the calculator. That is, the angle A is literally equal to the cosine inverse of this, or this is the same thing as saying, look, I am the angle that when you take the cosine of me, you get 4 over 6.4. So again, we say calculator, do a calculator. We say, all right, 4 divided by 6.4 equals, and we'll do cosine inverse. We need cosine inverse this time, about 51.3 degrees. So approximately 53.1 degrees. And we say, well, would this be reasonable to interpret this as being a 53.1 degree angle? Absolutely. It looks like this could be the case. And again, to find that top angle there, we say it is complementary with this angle right here. We just subtract 90 from it and make it positive. We say about 38.7. So B here would be about a 38.7 degree angle. We're just going to bury this last triangle here. Let's go again we say that this is isosceles. So we say this is 4 and this is 4. There's a reason why I included this as one of the examples, and the reason why is because these two acute angles, if they're opposite sides that are congruent in the first place, these two angles must be the same. And in a right triangle, there are only one way. There's only one way for these two acute angles to be the same. With this being a 90, these should be 45s. But just to go to show here, how about we work with angle A, which is this top angle up here? We could say, well, I need to relate A to these two sides, the opposite side and the adjacent side, so we'll go with tangent. We say tangent of A is equal to 4 over 4. So skipping straight ahead this time, we can actually say, well, I'm about to take the tangent inverse of both sides anyways, so I'm just going to be left with A on the left, and that would equal tangent inverse of the stuff on the right here. So we could say, well, A is approximately what my calculator gives me when I say tangent inverse of 4 over 4. Of course, 4 divided by 4 is 1, but if we do tangent inverse of this, it says, well, you are exactly 45 degrees. So I will switch this to an equal sign, but that's 45 degrees, and so therefore this angle C down here must also be 45 degrees. But again, just a few more examples of how to use inverse trig functions to back solve for angles. Cheers.